So apparently you want to solve some Newton's second law problems. It's gonna be a long one. It's gonna be a long one. It's gonna be a long one. This video, there are like 28 problems I'm going to solve of various different types. So stay tuned and use it as you need it. As with all videos, if you're watching a video and you're just watching all the way through and it's a problem series of videos like this one, you're not using this video correctly. So stop the video, solve the problem that is presented on the screen on separate paper. Don't just think about it, actually solve the problem. And then eventually you can get back and start the video again to check your work, or watch a couple of them and then solve the third one on a particular page. That's the way you should be using videos all the time. Stop them, go back, go forward. Oh, I know how to do these. Skip through the ones you know how to do and then move to the ones that you need. That's how you should be using this video. We're gonna start with an old meme, an old Star Wars meme. A lot of you like Star Wars, so it goes like, may the M.A. be with you. I can't stand it because M.A., right? It's supposed to, oh yeah, that's F equals M.A., so may the force be with you. Now here's the problem with what you may have read. Here's the problem with the form of Newton's second law that may have been presented to you. That F in F equals ma, that's supposed to be net force. So why don't we write net force? Net force equals mass times acceleration. The acceleration is the net force divided by the mass, because it is the net force. It's not just some random force, and that's one of the problems with our presentation, teacher presentation, textbook presentation of this equation, is that we really don't pay that much attention to the net force like we should. So keep in mind it's the net force, the vector sum of all the forces acting on an object. And there are going to be two G's here, G, you know, the little g, not the big G, but the little g, the acceleration of gravity as rounded off to 10, because it makes problems easier. 10 meters per second every second. That's not the same as the other G, which is the gravitational field strength in W equals mg. In W equals mg, G is 10 newtons of weight down for every kilogram of mass. So keep those things separate. You have acceleration. An object in free fall without air friction will accelerate downward at 10 meters per second every second. But the weight of an object is dependent upon the local gravitational field strength, which is 10 newtons per kilogram. Keep them separate. You'll have to use mass and weight and acceleration of objects and compare things in these problems. Free body diagrams showing one object and all the forces acting on the object necessary throughout. If you are not drawing free body diagrams on the easy ones, you're gonna have a lot of difficulty solving problems with the hard ones, so you do that. Plus some of the type on this is pretty small, so you wanna use a bigger screen for viewing this video because some of that type's pretty small in the problem presentations. Remember that Newton's second law is a vector equation. The acceleration that results from a net force is in exactly the same direction. And if you have an acceleration that is to the right, and you put a positive in for that, that means that the force to the right is also positive, and any force to the left would be negative. Keep that in mind. Use that for your directions and your positive, negative. It's a vector equation. Look closely at Newton's second law, and you will see that newtons is equal to kilogram meters per second squared, but newtons per kilogram is equal to meters per second squared. Keep that in mind. Another very important note. Mass and weight are different things. They're related by W equals mg, but they are different things. I keep on getting reports from college physics students. They're at the university, they're taking physics at the university, and they're annoyed at their professors who are supposed to be the experts in the physics who are confusing the words weight and mass. They use them interchangeably. They confuse the words scale and balance, and they use them interchangeably. Seriously? No, you can't do this, because in this series of problems, we will sometimes use weight, because weight's the force of gravity on an object. It is down, it has a direction, it is a vector. And in the same equation, we're gonna put mass. Mass, the resistance to acceleration, in this particular case, inertial mass in kilograms. They're measured on different instruments. They use different units. One of them's a vector, one of them's not. Keep them separate, okay? Just please. This is a scale, and this is a scale. These scales must not be used to measure mass. They're used for forces. Weight is the force of gravity on an object. Forces, in newtons, it's a vector, has a direction. This is for mass. Mass is the amount of matter in an object, or the resistance to acceleration. And this is for mass in kilograms, a balance for mass in kilograms. Keep the things separate, you might be able to solve the problems better. Our list of problems will include objects just moving horizontally in one direction, just moving horizontally, the normal force and weight, and force in the forward direction, maybe a friction force in the backward direction. And we're going to add some F equals mu times N. The friction force is equal to the coefficient of friction times the normal force. Add some of those problems in there. And we're also going to do vertical problems, free fall objects and free fall objects with air friction falling through the air or being thrown upward. Elevator problems, where you're standing on a scale in the elevator, you're looking for the normal force. And rocket problems and helicopter problems, things like that in the vertical direction. You tend to do those pretty badly. And add some inclined planes and do some other things toward the end that are more complicated, require a whole lot more math and some trigonometry. So this is one object, Newton's second law, one object, Newton's second law problems. Two objects or multiple objects, Newton's second law problems, that's for a later video. Let's learn physics. I've got my writing utensil, and I have my calculator, and I'm ready to go. So we've got a 100 kilogram cart pushed from rest with a horizontal 50 Newton force. Horizontal cart, horizontal cart. Okay, so these are all carts. They're on wheels, and they're being pushed in that direction. These things all have 100 kilogram mass, so it's 100 kilograms of mass. And the first one, this is really simple, but draw the free body diagram correctly, people. Here is that 100 kilograms. Here's the weight of 1,000 newtons, and the normal force of 1,000 newtons. Since there are no additional vertical forces, the normal force and the weight balance each other, and I will be using capital N for the normal force. Some of you will use capital F sub N, capital F sub G. I find this more convenient. That's what I'll be using. And pushed in some direction with a 50 Newton force, and that is the F. Now what you're tempted to do here is you're like 1,000 and 1,000 and a 50. Wait, they're all the same size. Be careful. Try to make this 50 obviously shorter. I didn't in this case. I'll try to improve. And there is no friction force. There's no friction. Find the acceleration, find the velocity 3 seconds later. So acceleration is unknown. That's what we're looking for. And the final velocity after 3 seconds. So Newton's second law, acceleration is equal to the net force divided by the mass, not just the force, but the net force. In this case, it's only one force, so 50 newtons divided by 100 kilograms. Notice that the 1,000 newtons and the 1,000 newtons don't come into this problem. This is a horizontal acceleration problem, so AX is equal to net force X over M. And you get an acceleration of 0.5 meters per second every second. Also called meters per second squared, but meters per second every second helps this thing make sense in that direction. It is a vector. It's a vector, so make sure it is a vector in your problem solution. Then the velocity at 3 seconds, if it starts at rest, so find the final velocity 3 seconds later. We're assuming it, push from rest, okay, it is push from rest. And then half a meter per second, half a meter per second, half a meter per second. Final velocity is 1.5 meters per second in that same direction. So that is number one. It's pretty simple, but get that free body diagram correct and practice the proper problem solving for the simple ones, and the harder ones will be easier. Number two, 100 kilogram cart pushed with a horizontal force of 100 newtons. If the friction force is 50, so now I've got a forward force and a backward force, find the acceleration and the velocity after 2 seconds if it starts at 5 meters per second. Start again with a free body diagram. You have the 100 kilograms and the normal force is 1,000 newtons because there is no other vertical force other than the weight and the normal, and both of those would be 1,000 newtons. Same size, you can use your little geometry tags to show that. This is the forward force, F is equal to 100 newtons. This is the backward force, the friction force is equal to 50 newtons. And same concept, acceleration is a net force divided by the mass because we are looking for the acceleration and the final velocity. Final velocity at 2 seconds if the initial velocity is 5 meters per second. We're assuming in that direction. Acceleration is net force divided by mass, 100 minus 50. So you can write this down, 100 newtons minus 50 newtons, or just write the 50 newtons to the right, divided by 100 kilograms. And that would be 50 over, oh, it's the same answer. It's a half or 0.5 meters per second every second in the direction of the bigger force. That's the acceleration. And then, okay, so initial velocity is 5. It picks up half a meter per second every second for 2 seconds. 5, 5.5, 6. So the final velocity is 6 meters per second in that direction. We good? Now number three, 100 kilogram cart accelerates at 5 meters per second forward with a 100 Newton friction force opposing the motion. Find the horizontal input force. Here is this thing, 100 kilograms. Normal force, again, the exact same thing, is 1,000 newtons. Practice the free body diagram, people. The weight is 1,000 newtons. And then the horizontal forward force is, I have no idea. And the horizontal backward force is F, I use a scripted F for the friction, 100 newtons. Okay, so two options. Here's the first one, which is more of an intuitive one. Net force equals mass times acceleration. Since I'm looking for a force, I can use a different form of the equation. They're all the same thing, but I just solve for net force in this case. Net force is, so the net force is equal to the mass, which is 100 kilograms, multiplied by the, the acceleration. The acceleration is 5 meters per second every second. So I know that this thing is accelerating at 5 meters per second every second in that direction. 5 meters per second every second, and that would be 500 newtons in that direction, and that is the net force. So you're tempted to say, oh, that's the answer, right? No. That is the combination of these two. And if you think about it carefully, that forward force, how big a forward force do you have to have such that the forward force and the backward force, when combined, would leave you with 500? These are going to partially cancel, right? So you think about it, you're like, okay, so 400 forward, 100, no, that leaves me with 300. 600 forward, okay, 600 newtons forward gives you the answer of net force of 500 back. Or, here's the other option, net force is equal to mass times acceleration. F minus 100 newtons is equal to 100 kilograms multiplied by 5 meters per second each second. F minus 100 newtons, forward force, backward force, minus, is equal to 500 newtons. Add 100 to both sides. F is equal to 600 newtons in that direction. Either one of those is entirely acceptable. This is the algebraic solution. This is the one that depends on the free body diagram and you drawing that thing correctly. I prefer this one, but this one is useful in other cases also. Some more horizontal motion. This is a cart looking for the mass. This is a cart looking for the friction force. This is a car. Okay, so cart, and car, similar ones. It's the same kind of situation. I want to be thorough here. So number 4, 200 Newton forward force, 100 Newton friction force. Cart goes from 10 to 25 in 3 seconds, find the cart's mass. So we have this thing where the M is unknown and the normal force, I don't know what that is because I can't find the weight because W equals mg. I don't know what that is, but I do know that these two are the same size. They do balance each other. 200 newtons forward, 200 newtons, 200. So the forward force is 200 newtons. And 100 Newton friction force, 100 Newton friction force. The cart goes from 10 to 25 in 3 seconds. Okay, so 10 to, oh, that gives me the acceleration, right? So think about it. Acceleration is 10 to 25. It's 15 and 3. That's 5 meters per second every second to the right. Just think about it and figure that out. No reason to use an equation, but it is delta V over T. 25 minus 10 is 15. Divided by 3 is 5 meters per second every second. Find the cart's mass. M is unknown, so these two will balance again, but the net force is equal to the mass times the acceleration. Okay, so net force. Oh, the net force is 200 newtons minus 100 newtons, or just write down 100 because you've found the net force, is equal to the mass times 5 meters per second every second, and 100 newtons is equal to mass times 5 meters per second every second, divided by 5, and the mass is 20 kilograms. Therefore, the weight would be W equals mg. M times 10 would be 200 newtons. This would be 200 newtons. And this would be 200 newtons also. There we go. That's number 4. Here's number 5. 20 kilogram cart. So we have a 20 kilograms. The normal force would be the same size as the weight. Those two are balancing each other. The weight is 200 newtons. The normal force is 200 newtons. And 500 Newton input force. So here is a significant, actually longer, F is equal to 500 Newtons forward. And the friction force is unknown. I don't know what the friction force is. 2, acceleration equals 2 meters per second every second forward. Now make sure that you remember these are free body diagrams. Forces only on these things, and the acceleration can be labeled near the diagram, but not on the free body diagram. Forces only. Find the friction force. Net force equals mass times acceleration. Right-hand side, 20 kilograms multiplied by 2 meters per second every second. And the net force would be 500 newtons minus F. And 500 newtons minus F is equal to 40 newtons, and negative F equals, subtract 460 newtons, and so F negative is equal to 460 newtons in that direction. So there's my friction force. Or, like I showed you before, net force is equal to mass times acceleration. That would be 20 kilograms times 2 meters per second every second. And so the net force would be 40 newtons in that direction. And for 40 newtons in that direction as the net force, that means that the 500 has to be 40 bigger than the back force. And so that would be 500 minus 40 gives you 460. Same answer. Now number 6, 1,000 kilogram car travels down the highway at a constant 50 meters per second. If the friction force is 3,000 newtons, what's the forward force? What's the normal force? Then you panic because you're not given the acceleration, and then you think about Newton's first and second laws, and you're like, oh, well, this is just a car, right? Here's a car traveling down the highway. There it is. It's a beautiful minivan. And the normal force would be this, and the weight would be that. Those two are balancing each other, of course. And then you're given the 3,000 Newton backward force, 3,000 Newton friction force. You're looking for the forward force. Oh, wait, it's a constant velocity. Acceleration is 0. Forward force is 3,000 newtons. Normal force would be the same size as the weight. The weight is 10,000 newtons. W equals mg, where g is 10, so the normal force is 10,000 newtons. And they're that and that. They're your answers. That's it. Simple. Constant velocity. Look for that. All right, now these are not free fall problems. The first one is free fall supposedly designated as only the weight is acting. But anyway, this is no air friction. This one has air friction. This one has air friction. And this one has air friction. Dropped, dropped, dropped. And dropped. Find its acceleration and speed. And this one is thrown upward. So these are all vertical problems. Keep in mind that the weight does exist. So number 7, we start with that. 60 kilogram boulder dropped in the absence of air friction. 60 kilograms dropped, weight 600 newtons. Acceleration is net force divided by the mass, and 600 newtons divided by 60 kilograms. Acceleration is 10 meters per second every second down. We knew that one already because it's in free fall. There's no friction. The only force acting is the weight. And if you take weight divided by mass, because weight is mg divided by the m, you're going to always end up with the g as long as there is only the weight acting. Number 8, here we add a complication. This is a 60 kilogram mass. Again, that is a 600 Newton force. That's the weight. And then 500 Newton air friction. 500. Make it shorter, but not a ton shorter and not obviously shorter. Just draw it shorter. 500 Newtons. This is a visual cue showing you that this size is smaller than that size. You're looking for the acceleration. Acceleration and the final velocity is 3 seconds later at 3 seconds. And acceleration is the net force divided by the mass. Net force is 600 newtons down minus 500 newtons up is divided by 60 kilograms. And so it's 100 newtons down divided by 60 kilograms. 100 over 60, 1 2/3. This is 1.67 meters per second every second down. Not the acceleration of gravity anymore because of that large friction force. Find its acceleration and speed 3 seconds later. Speed 3 seconds later. 1 2/3 time 3 seconds starts at rest. And 1 2/3, 3 1/3, and 5. So the final velocity would be 5 meters per second down. Pay attention to these directions. I prefer arrows. Number 9, a 60 kilogram boulder falls with a 600 Newton air friction force. Acceleration and speed 3 seconds later, same thing. These are all exactly the same problem. 60 kilograms, 600 newtons air friction, 600 newtons weight. Oh, there we go. So this thing, the acceleration would be net force divided by the mass, 0. Oh, the acceleration is 0 meters per second every second, or just 0. It doesn't exist. This is falling at what we call terminal velocity, where the acceleration is 0 because the friction force balances the weight. And this one, no friction. Acceleration is 10 meters per second every second down. This one, lots of friction, 1.67 meters per second every second down. And this one, they balance, and so there's no acceleration. And then number 10, this one is thrown upward. So 60 kilogram boulder, initial velocity is 50 meters per second upward. 900 Newton air friction, acceleration, and speed, final velocity is, I don't know, at 3 seconds. Free body diagram again. Always start with the free body diagram after you have read that thing carefully. The weight, 600 newtons. And then the air friction force. The air friction force, you're tempted to put it up, right? Because you did the other 3 up. Well, this one and that one up. No. This one is going upward. And if it's going upward, the air friction is going to be exactly opposite that. So this is going to be the air friction force. There's the friction. That's 900 newtons. And so the total force acting on it is a 1,500 Newton force down. Look at that. The acceleration is greater than the acceleration of gravity when you throw something up, because the air friction and the weight are acting together. And the acceleration is net force divided by the mass. Net force would be 1,500 newtons down, divided by the mass of 60 kilograms. And 1,500 divided by 60 equals 25. Acceleration is 25 meters per second every second down. So there are plenty of cases in which the acceleration of an object can be greater than the acceleration of gravity, just not in free fall if there is no air friction. 25, if it starts at 50, I want to find the final velocity at 3 seconds. It's gone up to the top, it's come back down. So I would say that the final velocity would be 25 meters per second down, because 3 seconds at 25, 75 minus 50 gives you that. The only problem is that neither this one nor this one, those are not going to be answers, because this air friction force is not constant. As you pick up speed, you get more air friction force. As you lose speed, you get less air friction force. At the very top, this thing doesn't have any air friction, and this calculation assumes a constant air friction. So these last parts, speed 3 seconds later, speed 3 seconds later, Speed 3 seconds later. Yeah, they're not exactly the best. This one is because there's no acceleration. They're not good questions, so watch for those. All right, a little more complicated this time. A 30-kilogram lawnmower. Some of you have never pushed a lawnmower nor paid attention when one was being pushed, so you're not going to even see this. So you sketch the picture first before you draw the free body diagram. That can help a lot too. 300 Newton force at 30 degrees below the horizontal. What do you mean below the horizontal? I'll show you in the picture. At a constant speed, find the friction force from the muddy ground. Okay, so 30-kilogram lawnmower, and you can start your little lawnmower like this. Here's your lawnmower. Put a block on top of a block. You can make that into a car, right? You can make that into a tank, or you can make it into a lawnmower. So here's the lawnmower. This is at an angle of 30 degrees. Here's your 30 degrees. And a good practice is to like underline things, 300 Newton force, 30 kilograms, underline things in the problem. So that's 30 kilograms, 30 degrees. This is a 300 Newton force in that direction along the handle. Now this is not a free body diagram, that's a sketch. So then sketch the free body diagram separately. Here is that thing, this is 30 kilograms, make it nice and long, and that's not 301, sorry, 30 kilograms, and the weight would be 300, weight of 300 newtons, and then the normal force, you're tempted to make that 300 newtons, but no. This thing right here is pushing partially down. So the normal force is not 300 newtons. Weight on that one. Now 30 degrees below the horizontal. We tend to draw the free body diagrams, the forces on the free body diagrams from the object outward. So they look like that. This is a 300 Newton force, 300 newtons, and it is at 30 degrees below the horizontal. So whenever you see one of these things that is not on the axis, you must find the two components. There's the right angle, and the quickest way to find those components is to take your 300 cosine 30, enter, 300 sine 30, enter, get those two values. This is 260 newtons, and that is 150 newtons. Or you could have realized that this was a 30, 60, 90 triangle, and that 30, 60, 90 triangle, 300, half of the 300 is the short leg, and then take the short leg and multiply by the square root of 3 to get the long leg. The question is constant speed. Watch for that. Oh, that means that there is zero, acceleration is 0, and therefore the horizontal force back here would balance the horizontal force in the forward direction. 300 newtons. Once you have the 260 and the 150, these components act as replacements. You can lightly cross that thing out to remind yourself that, oh, instead of the 300, I'm dealing with the 260 and the 150. So the backward force, the friction force, not really technically a surface friction force because it's muddy ground and it's sinking in. But anyway, 260 newtons in that direction. So that is one answer right there. Those two will balance each other. Those two balance. And then in this direction, the vertical direction, 300 and 150, those two are acting in the same direction. Both of them are down. Then it must be balanced by the, oh, this normal force is actually bigger. It's actually bigger than the weight by a lot. And so the 150 and the 300 must be balanced by the 450 newtons in the upward direction. So that is the answer for that one. Constant speed, 0 acceleration, balanced forces forward and backward, balanced forces up and down. Don't forget this one. Number 12. If a 150 kilogram sled on a horizontal surface is being pulled with a force of 200 newtons at an angle of 37 degrees above the horizontal. Lots of words. So then you draw the little picture. You got the sled, right? You got the little human on it because this is maybe two humans. Put two little humans on there, and you get to pull the thing. You're pulling this thing with see 200 newtons at an angle of 37 degrees. 37 degrees. That should be a dotted line above the horizontal, and that should be greater than that. But make sure that you show this thing less than 45. 150 kilograms, 150 kilograms here, and 37 degrees. Sled accelerates at 3 meters per second every second forward. Acceleration of 3 meters per second every second forward. What's a friction force? So the friction force is unknown. All right, So it accelerates. Okay, so this is a horizontal problem. The vertical forces, we're going to balance them in the free body diagram, but they're not going to matter in the problem because we're looking at a horizontal acceleration because this is a sled. It's not jumping off the ground and it's not digging into the ground. There's the ground, not the free body diagram. Here's the free body diagram. This thing is 150 kilograms. And then the weight, here's the weight of 150, 1,500 newtons for W equals mg. This one, contrary to this one was pushed into the ground a little bit. This one's lifted off the ground. So the normal force is actually going to be smaller. And here is the forward force of 200 newtons. Smaller than 1,500, 200 newtons forward. Here's the x component. Here's the y component. Here's this 37 degrees. Make sure your diagram is relatively large so you can see everything. You know that the friction force backward, which is what we're looking for, is going to be smaller than that x component. Then you take this thing, 200, 37 degrees. Don't even need this little thing right here. 37 degrees means a 3, 4, 5 triangle. 40 times 5 is, and then 40 times 3 is 120 newtons, and 40 times 4 is 160 newtons, and 1,500, 120, 120 plus what? Plus 1,380. So this normal force is 1,380 newtons. Don't have to find it, but it's always good to find everything to practice. So 1,380 plus 120 balances to 1,500. And then 160, I've got to find that force. Okay, so net force is equal to the mass times the acceleration. 160 newtons minus F is equal to mass 150 kilograms times acceleration of 3 meters per second every second. 160 newtons minus F is equal to 450 newtons. And then minus F is equal to 150, 300, 290 newtons. So the friction force is 290 newtons. So you think the friction force is backward. That's 290, right? So you caught my mistake too? Oh, wait, the friction force is negative 290, which means that, wait a minute, look at this number. That's the net force, right? That 450? Mass times acceleration is the net force. So I need 450 newtons to cause the given acceleration of 3 meters per second every second. That's not possible with the friction force. That's not possible with this 200 Newton force. I need an additional 290 newtons forward to cause that. So it's not a friction force. I need 290 newtons forward more. That says more. So there's your answer. There is no friction force. You need 290 additional newtons forward. Now we're back to vertical problems. The other one's air friction and weight, right? When you had that 60 kilogram ball. With helicopter, elevator, and rocket problems and the ball falling, they're all the exact same kind of problem. Don't let the different object confuse you. When you're drawing a helicopter, make sure you draw the helicopter correctly. Here's the proper drawing of a helicopter. You got that, you got the tail rotor. This is required for Newton's third law. Then you have this top rotor here, like that. And then you have the little skids, which the only reason they have those little skids is exclusively for, it's not for landing this little helicopter. Those are for stuntmen to like hang off in the really cool action movies. Anyway, 1,000 kilogram helicopter rotor provides a thrust. That's just the force from the air up on it of 11,000 newtons. Find the acceleration and the velocity after 5 seconds. It's initially at rest. Okay, so 13, helicopter. Here's my helicopter. 1,000 kilograms. The weight is 1,000 newtons. Just don't forget that, because that's what you're going to forget. 11,000 newtons. 11,000 newtons. The thrust is 11,000 newtons. You can call that an F if you want to, whatever. But you have to remember that it's bigger. It's actually bigger than that. So you should draw it longer. I didn't do a very good job of that, but whatever. And this is not 1,000. This is 10,000. 10,000. 10,000 newtons. 1,000 kilograms, W equals mg. Okay, find the acceleration. Acceleration is unknown, and the final velocity is, I don't know, after 5 seconds. acceleration is the net force divided by the mass. 1,000 newtons upward divided by the mass of 1,000 kilograms. And the acceleration is 1 meter per second every second up. One answer. And at 1 meter per second increase in speed up, 5 seconds later, final velocity is going to be 5 meters per second up. Number 14, 1,000 kilogram helicopter rotor provides a thrust of 8,000 newtons. Acceleration velocity after 5 seconds, it's initially at rest. So same problem, but a thrust of 8,000 newtons. Now, be careful when you're solving these problems because you are tempted just to use the given force. He's like, oh, well, that's F equals ma, right? 8,000 newtons equals, and you get 8 meters per second per second. No, because you're not drawing the free body diagram. Here is the 1,000 kilograms. We have to make those objects bigger. Here is the 10,000 Newton weight, and here is the significantly shorter thrust of 8,000 newtons. And you're like, oh, it's going to accelerate downward. Acceleration is net force divided by the mass, 2,000 newtons down, divided by 1,000 kilograms. Acceleration is 2 meters per second every second down. That's one answer. 5 seconds later, velocity after 5 seconds initially at rest. Final velocity is 5 times 2 is 10 meters per second down. Number 15, a 1,000 kilogram helicopter hovers 1,000 meters above the ground. Find the thrust provided by the rotor. Wait, what's this 1,000 meters thing? We haven't dealt with that. Find the, 1,000 kilogram helicopter hovers at 1,000 meters above the ground. Find the thrust provided. I don't know, what's the acceleration? English word hover. Okay, so same free body diagram, but just ignore that. If you have a weight of 10,000, the thrust, the force, and the weight have to balance each other. And so that's going to be 10,000 newtons up, static equilibrium, staying right there. 16, acceleration is 0. 3 metric ton rocket accelerates upwards at 3G. What is that 3G? Is that like 3G, 4G, and 5G speeds on my phone? No. This is 30 meters per second every second because it's 3 times the acceleration of gravity. Upward. So I know that the acceleration is 30 meters per second every second upward. And that means you weigh about 3 times as much as you would. That's why they're strapped down into their seats like they are in the rockets. 3 metric ton rocket, mass is 3,000 kilograms. A metric ton is, of course, 3,000 kilograms. Well, okay, 1 metric ton is 1,000, and 3 is 3,000. Find the engine thrust. So draw your beautiful little, just your rocket, because this is rocket science, people. And the thrust force, the force upward, and the weight. I know that thrust is going to be much bigger than the weight. Weight is 30,000 newtons. So multiply by 3, right? 3 times 3 is 90,000. I could write 90,000 there. No, don't do that. Just don't. Just please think about this stuff a little bit and use the equation. Net force is equal to mass times acceleration. And anyway, okay, the problems, you're going to ignore this and then just find the force, and you get 90,000. You're going to take 30,000 times 3 because it's 3 times g, so it's 3 times the weight, right? You're going to get 90,000. Neither of those is the answer. 3,000 kilograms is equal to the mass times acceleration is 30 meters per second upward, which is 90,000 newtons upward. That's the net force. The net force, which means that this upward force minus the downward force has to give you, this is what you're looking for, upward force minus the downward force, it's going to have to give you 90,000. And so it's 120,000 newtons up. 120,000 newtons up minus 30,000 newtons down. 120,000 newtons up minus 90,000. Oh, there's the net force. Or from here, the F minus 30,000 newtons is equal to, from here, 90,000 newtons, and F equals 120,000 newtons up. Either way, get the same answer. more algebraic, more linked to the diagram that you drew. All right, elevator problems. These are the same problems as the rocket, as the helicopter, as the ball falling, moving up and down. In this case, it is you, and then in this case, her. So we're looking at you. You need to know your mass. My mass at 220 pounds, my mass is 100 kilograms. I'll use that one. Your numbers will be different. Downward at a constant velocity in an elevator, what's the reading? Accelerate upward in an elevator at 3 meters per second every second. Accelerate downward in an elevator at 2 meters per second every second. And then this thing here. So starting with the situation, here is the situation. You are, well, you're really tall or the elevator is really short. You're standing on a scale and you're looking for that scale reading, which represents the normal force. So the scale represents the normal force, which according to Newton's third law, there's a force upward on you from the floor and a force downward on you from you on the floor. So that interaction, the floor to you and you to the floor, that is represented by the scale reading, and that's the normal force. There are actually two normal forces, one on each object in contact. We're interested in the normal force that is up on you. So you travel downward at a constant velocity, and my mass is 100 kilograms. And for number 17, I draw my free body diagram. This elevator, you, scale, 3 objects, not a free body diagram. So here's me as a box, 100 kilograms, all the forces are up and down. My weight is 1,000 newtons. This one's, constant velocity, 0 acceleration. That means that the normal force has to balance the weight, and that is 1,000 newtons. Number 18, you accelerate upward in an elevator at 3 meters per second every second. So here's the elevator, here's you in it. You are accelerating upward. So we're accelerating upward, which means you could have a velocity downward, like you're slowing down, or you could have a velocity upward, up arrow, or your velocity is upward and you're speeding up. So you either hit the button to go up and you're accelerating upward, or you're reaching the bottom, you reach the bottom and you're slowing down. Velocity down, acceleration up, or velocity up, acceleration down. This gives you no information as to the direction of your velocity. What's the apparent weight reading on the scale beneath your feet? Apparent weight is the same as the normal force. Here is you in your free body diagram again, 100 kilograms. Your weight is still exactly the same, 1,000 newtons. And then, let's see, upward. Ah, man, messed up my diagram here, huh? But you have to remember that the normal force is going to be bigger. And so the net force is equal to the mass times acceleration, 100 kilograms times 3 meters per second every second up. And that's going to be 300 newtons in the upward direction. That's the net force. It's got to be bigger. So 1,000, it's 300 newtons bigger than 1,000. So the normal force would be 1,300 newtons upward. Or the apparent weight would be down, I guess. But its normal force is 1,300 newtons up. And the force from your feet on the floor would be 1,300 newtons down. 1,300. Wait, 1,000, 1,300, 0 and 3. We're noticing a pattern here. Number 19. You accelerate downward in an elevator at 2 meters per second every second. So same situation. You're in the elevator. Here's you. You're the same size. You are now accelerating downward. So the acceleration is down. Now you could have an initial velocity upward, or you could be moving up. And if you're moving up, you're reaching your intended floor and you're slowing down. So you're moving up and slowing down once you reach your floor. Or your velocity is downward and you just hit the button and you're accelerating down. Either one of those velocity situations will give you this acceleration. What's the apparent weight reading the scale beneath your feet? So here we have you again. It's me. And the weight, always do the weight first because you know it, W equals mg, and 1,000 newtons. I'm accelerating down, which means that my normal force has to be smaller. Don't know what that is. You know that the down force has to be bigger than the up force for a down acceleration. Net force is equal to mass times acceleration, 100 kilograms multiplied by the acceleration of 2 meters per second every second down, and that would be 200 newtons down, which means that the normal force would be 800 newtons total, so that I get 1,000 newtons down, 800 newtons up, leaves me with a net force of 200 newtons down. Now you see the pattern? If there is zero acceleration, the weight is the same size as the normal force. And if you think about it, you're like, all right, so this one's going to accelerate upward. Normal force is bigger. By how much? By 3g, or 3/10 of a g much, 3 meters per second every second. 13 times 100 gives you 1,300. And it's got to be bigger. You know it's bigger. And then this one, weight is down, normal force is up, it's got to be smaller. 10 minus 2 is 8. 8 times 100. 8 times 100 is 800 newtons is the up force. There's a quick shortcut from any of these things. And then number 20. Number 20, accelerate. The elevator floor applies a 400 Newton upward force. So here she is. This is her mass. This is her upward force, 400 newtons. That is the normal force. Pick up speed in the down direction. Oh, the acceleration is down from 2 to 6 in 2 seconds. 2 to 6 is 4 meters per second change in 2 seconds, which is 2 meters per second every second. And so this would be bigger. So her weight is larger than the normal force. Acceleration is down. And when you're solving problems like this is a vector equation, of course. And so the force, the bigger force, which is in the direction of the acceleration, would be the positive number. Whatever the direction of the acceleration is, that is the positive direction. So it's weight minus 400 newtons is equal to the mass times 2 meters per second every second. And you're like, wait, I don't know weight. I don't know what the W is, and I don't know what M is. That's two unknowns, one equation. I can't solve it. But then you're like, of course, W is mg minus 400 newtons is equal to mass times 2 meters per second every second. Wait, mass. But now I have g. Oh, wait, but g is just the same number we dealt with before. G is 10 newtons per kilogram. So this is mass times 10 newtons per kilogram, which is the same as meters per second every second, minus 400 newtons is equal to m times 2 meters per second every second. 10m minus 400 newtons is equal to 2m. 8m is equal to 400 newtons, and m is equal to 50 kilograms. Let's go back and check it. 50 kilograms, that's 500 newtons down, so this would make that 500 newtons. 500, 400, that's 100 newtons of net force divided by 50 kilograms. That would be an acceleration of 2. Got it. We're good. Top view, we're looking at the thing from the top. Two forces act on a 100 kilogram object. Here is the 100 kilogram object. Find the acceleration. Forces are 6,000 newtons west, 6,000 newtons west, and 3,000 newtons south. 3,000 newtons south. All right, so net force equals mass times acceleration, correct? It's a right angle, so I'm going to add those two, right? So 6,000 newtons and 3,000 newtons gives me the hypotenuse and this angle. Got to put those together. The quickest and easiest way to put those together, first of all, you draw the first vector. At the head of that first vector, you draw the second vector, and then the resultant is from here to here. So that's down in that third quadrant between 180 and 270 degrees for our standard math trigonometric direction system. All you have to do is take your little calculator and, so the Pythagorean theorem, the square root of the quantity 6,000 squared plus 3,000 squared equals 6710. So 6,710 newtons is the net force. And then that little angle in there, tangent. Tangent is opposite over adjacent, right? So the inverse tangent of 3,000 divided by 6,000, or 3 over 6 or 0.5 would give you 26.6 degrees. That right in there, that is 26.6 degrees. And if that's 26.6 degrees, then 180 plus 26.6 is 207 at 207 degrees. That's the net force. Now we want the acceleration. Acceleration is the net force divided by the mass. Net force is 6,710 newtons at 207 degrees divided by 100 kilograms. That would be 67.1 meters per second every second. That is an acceleration. It's like almost 7g at 207 degrees. All right, so now I've got some more complicated ones. This physics is fun, right? So we're using the friction force equation. Lowercase f is equal to the coefficient of friction times the normal force in two separate problems here. A 100 kilogram toboggan has a bottom surface of waxed wood and is being dragged along a snowy surface. Find the horizontal forward force necessary to cause the toboggan to accelerate at 1 meter per second every second forward, we'll assume. And okay, so number 22, draw the toboggan. Got the toboggan with the little people on the back end. This is a 100 kilogram toboggan. Bottom surface being dragged along a horizontal forward force. Horizontal forward force, don't know what that is. It's on a surface here. And necessary acceleration is 1 meter per second every second forward. Okay, so free body diagram, 100 kilograms, the normal force and the weight, normal force. No additional forces in the vertical direction, so 1,000 newtons balances the 1,000 newtons of the normal force. Forward force is, let's see, forward force, I don't know what that is. So that's the unknown. Friction force is going to be backward, and that is where we're going to use the coefficient of friction times the normal force. Now we need the coefficient of friction. Coefficients of friction, right here, rubber on concrete, rubber on concrete, rubber on ice, ski on, that's close enough, 0.05 and 0.14. So the static coefficient of friction, is 0.14, and the kinetic coefficient of friction is 0.05. Those are the ratios of friction force to normal force. We're assuming waxed ski on snow. Good enough. And then we need the coefficient of friction times the normal force. It is accelerating. So we know that it's not the static, it's sliding. Since it's sliding, it's actually sliding along the surface, it's got to be the kinetic. So that would be 0.05 multiplied by 1,000 newtons, and that's 50 newtons is the friction force. So net force is equal to the mass times the acceleration. The forward force minus 50 newtons, if you want to use the algebra method, is equal to the mass, 100 kilograms, multiplied by 1 meter per second every second. F minus 50 newtons is equal to 100 newtons. That's the net force. And so F is equal to 150 newtons in the forward direction. That 150 overcomes the 50 backward. 150 overcomes the 50 backward and leaves you with a net force of 100 newtons. Checks. All right, number 23. A 2 metric ton car is traveling on dry concrete at 60 miles an hour. 23. Car. Here's your little car traveling at 60 miles an hour. That's the velocity. Slams on his brakes and slides to rest. That's the initial velocity. The final velocity is 0. Find the maximum acceleration. Acceleration is unknown, and the time to stop is unknown. Well, if you look at your reference tables and all your conversion factors that you have, 1 meter per second is 2.24 miles per hour. So if I take that the 60 miles per hour and divide by 2.24 to get me a smaller number. 60 divided by 2.24 equals 26.8. 26.8 meters per second. All the values have to be in meters per second. And let's see, what's the acceleration? This is a car traveling on dry concrete, 60 miles an hour, slams on its brakes and slides to rest. Maximum acceleration. So car on concrete, rubber on concrete, dry, which is preferable, kinetic versus static. We don't want the kinetic, we want the maximum acceleration. So that'd be a static of 0.9. Coefficient of static friction is 0.90. That's the one we're going to use. The 23 2 metric ton car, that's 2,000 kilograms. Here is the free body diagram, 2,000 kilograms. The weight, 20,000 newtons. No additional vertical forces. Those two are the same size. This is the normal of 20,000 newtons. And then sliding to rest. Velocity is forward. Oh, the only force is the backward friction force. There's no forward force. What do you think? You're going to keep on the gas while you brake? Well, you shouldn't be doing that. You switch your foot from the gas pedal on the right to the left-hand side, and you get the friction force, coefficient of friction times the normal force, which is 0.90 multiplied by 20,000 newtons from up here. And 18,000 newtons is the force, and that would be the net force also. Acceleration is net force divided by the mass, which is 18,000 newtons backward divided by the 2,000 kilograms. Acceleration is 18 over 2 is 9 meters per second every second, 0.9 g in the backward direction. If it starts at 26.8 meters per second and ends at 0, it's slowing down at 9 every second. It's about 27. It should take about 3 seconds to stop. 9 times 3 is 27. There we go. All right, more friction problems. Still on a flat, These are assuming horizontal. A drag car has just done a burnout to warm up its tires. You do that little burnout, spin the tires, it warms up the tires, increases the coefficient of friction. The resulting coefficient of friction is 2, not something less than 1 like all these things are, but these coefficients of friction can get above 1, even though it's kind of rare. What's the maximum acceleration of the car? I don't know. Okay, what are we going to do? Quick little sketch. 24, you got the little drag car, right? Here's your drag car. And you got the little big wheels out back, and the wing. There's a little wing, and here's a little guy, and then here's a little wing up front. And that thing is going to accelerate. Now this is the rear wheel. That's the one where the coefficient of friction is pretty high. Coefficient of friction is 2. No units. It's a ratio of the friction force to the normal force for a particular surface combination. And you're looking for the acceleration. Oh, well, free body diagram, right? Wait, I don't have the mass. Do the free body diagram anyway. It's m, right? So this is weight. Well, what is weight but mg? Yeah. This is all horizontal and vertical forces, and so that balances that. The normal force is also equal to mg. And then the forward force is going to be, at least at the beginning, the only force applied. So that is going to be the forward force, which is the friction force between the tires and the road. And all I have to do is calculate the friction force for the net force for the forward force. And that would be the coefficient of friction times the normal force, which is 2 times mg, which is 2mg, which is 20m. Okay, so that's the net force, right? So acceleration is net force divided by the mass. That's 20m over m. Oh, there we go. The mass divides out. That's how that works. That is really nice. You could also just do the there's the 20. Acceleration is 20 meters per second, which is 2g. That's the answer. You could also do net force divided by the mass, which is 2mg from the coefficient of friction times the normal force divided by m. The m's divide out. 2 times 10 is 20. So that's how that problem works. Sketch the free body diagram anyway. Fill in the pieces that you know. Use the equations that you have and the basic relationships that are there, and then realize that, oh, well, it's friction force. Friction force is coefficient times normal. Normal is the same size as the weight. The two balance each other. There we go. That works. Similar problem number 25. A car is slowing down on dry asphalt. Who cares if it's dry asphalt? Oh, dry asphalt. Let's say, so rubber and asphalt dry, slowing down. Find its maximum. You're looking for the big numbers. Rubber on asphalt, asphalt dry, 0.85. 0.85 is the number. Coefficient of friction is 0.85. This thing has a mass of m. Its weight is mg. The normal force is mg. It's moving in this direction. So it's the velocity is that way, acceleration is that way. Therefore, the friction force is opposite the motion. And net force equals mass times acceleration. Friction force equals mass times acceleration. Coefficient of friction times normal force equals mass times, that's acceleration, not g. And then coefficient is 0.85. mg is the normal force. A is equal to 0.85 g, which is 8.5 meters per second every second backward, slowing at 8.85 meters per second every second. That's how it works. If you don't have I don't have any information, I can't. Just W equals mg. Set it up that way. More complicated. A 150 kilogram wooden sled on a horizontal wooden surface. What? How is it wooden on the? Oh, that's because it's on the list here. Wood on wood. Okay, we'll get back to that in a minute. Is being pulled with a force of 2,000 newtons at an angle of 37 degrees above the horizontal. What's the acceleration of the sled? Similar to a problem we did before. Here's a surface. Here's the sled with the. Anyway, so there's the sled. You're pulling this thing along with a 2,000 Newton force. An angle of 37 degrees above the horizontal, 150 kilograms. What's the acceleration of the sled? The coefficient of friction in this case would be, let's see, coefficient of friction, wood on wood acceleration. Wood on wood acceleration, the coefficient is kinetic is 0.30, and the static is 0.42. Okay, got those numbers right there. Then 150 kilograms, weight 1,500 newtons. Normal force. Oh, wait, it's not the same because this thing is pulling up a little bit. So 2,000, 37 degrees. 37 degrees, oh, it's a 3, 4, 5 triangle pretty much. 50 times 40, 1,600. Sorry, 1,200. That's the short side. 1,600 is the long side. You can also take this thing, 2,000 cosine 37, enter. 2,000 sine 37, enter. It's 1,600 and 1,200. Then what's the acceleration? This is the, I'm not going to use that one because I have the two replacements. I know that 1,500 and 1,200 leaves me with a normal force of 300, right? 300? 300 newtons. 300 plus 1,200 gives you 1,500. The two ups balance the down. Then this friction force in the backward direction is the coefficient of friction times the normal force. So friction force, this thing is going to accelerate. And what is the coefficient of friction? It's going to accelerate 0.3. 0.30 multiplied by 300 newtons. Not the weight, multiplied by the normal force. That would be 3 times 3 is 9. 90 newtons is the friction force. Wow, that's really small. You lift up on this that much, and the friction force is going to be quite small, so you don't get much of an effect. It's definitely going to accelerate, by the way, because the 0.42 gives you like 130, which is very small compared to the 1,600 newtons.
And then the acceleration, A, is equal to net force divided by the mass. That would be 1,600 newtons minus 90 newtons, forward minus backward, divided by the mass of 150 kilograms. So 1,600 minus 90 is 1,510. 1510 divided by 150 equals 10.1. Acceleration is 10.1 meters per second every second in that direction. Here's a crazy one. A 2 metric ton car is accelerating up a 5-degree incline at half g, which is 5 meters per second every second, and it is up the incline with a forward force of 15,000 newtons. Find the friction force. We're not given a surface, no surface given, so we're not using these coefficients of friction. That's not a part of it. Accelerating up an incline. So the incline is small, so it's a small incline, looks like this. This angle is 5 degrees. 5 degrees is actually significantly smaller than that, but you have to be able to show this. Car, here's your little car accelerating up the incline. Of course it's floating, but the acceleration is 5 meters per second every second in that direction. Forward force of 15,000 newtons. That is 15,000 newtons forward. That's the forward force. Find the friction force. F is unknown, 2 metric tons, 2,000 kilograms. All right, so anytime we have an inclined plane, you make sure that you draw the x-axis parallel to the incline and the y-axis perpendicular to the incline. And then the weight is still perpendicular to the ground. It's straight down. It's not perpendicular to the surface, but the normal force is perpendicular to the surface because normal means perpendicular. 20, the weight is 20,000 newtons. And now you want the component that is parallel to the incline, looks like that, and the weight that is the component that is perpendicular to the incline that looks like that, and your right angle is right there. This angle is the same angle as the 5 degrees. You lift that thing up that much, and you rotate the whole thing 5 degrees. So that would be 5 degrees right there. And then the normal force, that normal force is going to balance this. So that and that are going to be the same size. Find the components of it. Do the same thing as we did before. 20,000 cosine 5. 20,000 sine 5, and you have a 19,900 and a 1740. There's a 1740 that is in this direction, is pulling it down the incline, and 19,900, and this is 19,900. We don't need it in the vertical direction, but we will use this 17,400. Sorry, not the vertical, the perpendicular direction. And forward force of 15,000 newtons. So big forward force, 15,000 newtons. 5 degree incline at 5. Okay, so acceleration is the net force divided by the mass, or net force is equal to mass times acceleration. And the net force, forward force is 15,000 newtons. Backward force, 1740 minus 1740 newtons. Minus the friction force. Oh, there's a friction force that I forgot to draw here. Friction force is backward. Forward force, friction force is backward, and that x component is opposing the forward acceleration, is equal to the mass, which is 2,000 kilograms, multiplied by the acceleration, which is 5 meters per second every second. 15,000 newtons minus 1740, probably should have subtracted that, is equal to 10,000 newtons. So let's see, 10,000 minus 15,000 minus 1740. 10,000 minus 15,000 plus minus to the other side 1740 equals 3260. Negative F equals negative 3260 newtons. Don't drop the negatives, you tend to. So the friction force is 3,260 newtons in that direction. Parallel to the inclined plane as shown here, and that 3260 plus the 1740 gives you 5,000, because the 10,000 newtons is the net force. Now find the acceleration of a 3 kilogram wood block beginning at rest. Wood block on a wooden inclined plane, 20 degrees. Okay, so a little bit steeper this time. Make sure that you show it less than 45 degrees. That is 20 degrees. Here is a 3 kilogram wood block on that surface. You're looking for the acceleration. Free body diagram first, parallel to the incline, perpendicular to the incline. Try to draw these things well. It's kind of difficult to do. And then the weight, 30 newtons, is the weight. And then this is parallel to the incline. This is perpendicular to the incline. Weight component, perpendicular, weight component, parallel. This angle, of course, is the same as the angle from the horizontal. And so you take 30 newtons, 30 times the cosine of 20, cosine 20, 30 sine 20, and you get 28.2 and 10.3. Here, this is the normal force. Normal force is defined as the force perpendicular to the surface acting on the object, as opposed to the 28.2 newtons. And then this should be parallel to that. And then, okay, so find the acceleration. Oh, friction force. Friction force in this direction. I don't know what that is. So I'm going to calculate the friction force. Friction force is the coefficient of friction times the normal force. It's going to accelerate. So we use, what are those values? Wood on wood. 0.3 and 0.2. Coefficient of friction, 0.3. Coefficient of friction, 0.42. This is the static, and that's the kinetic. It's going to accelerate. So look at that 0.3. 0.30 times the normal force of 28.2 newtons. Again, the normal force is the force perpendicular to the surface acting on the object and is not necessarily the weight, but you're always told it is, or you always feel like it is. And 0.3 times 28.2, 28.2 times 0.3 equals 8.46, 8.46 newtons. 10.3, okay, that looks good. And you have 8.46 and a 10.3. The acceleration is the net force divided by the mass, and that net force is 10.3 newtons minus 8.46 newtons divided by mass of 3 kilograms. 10.3 minus 8.46 or 8.5 is 1.84 divided by 3 is 0.61 meters per second every second in that direction. There's the acceleration. But wait a minute. Is that thing going to accelerate? Oh, so this one, if you place it there in that location, this thing might not actually accelerate. So let's find the static friction and then see if it's bigger than the 10.3 to see if this even actually happens. All right, so friction force, coefficient of friction times the normal force. This is the static, that's the break loose. This is the kinetic. That assumes it breaks loose. So 0.42 times 28.2 newtons is 0.42 times 28.2 equals 11.8 newtons. It's the friction force. Wait a minute. If I have 11.8 and a 10.3, friction force is bigger. It will not break loose. So this answer, inappropriate, will not begin to accelerate. The plane has to be steeper to get it to break loose, or you have to just push it a little bit to get it going. And then the acceleration will be 0.61 meters per second every second. There we go. 28 problems. Longest video on Newton's second law in my history, and my longest video ever. Congratulations for watching to the end. You should go eat a chocolate bar or something. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.